All right, so let's start. Let's start with the graph of y equals cosecant of x, and let's take a look at what that's going to do. The graph of y equals cosecant of x, again, as we said, is related to the sine function. So if you know this reciprocal identity, it's not hard to deal with the idea of what that looks like for us. So what I'm going to do is I'm going to go ahead and I'm going to graph the sine of x function and use it as a guide to help me get my cosecant. So let's start off. We know what y equals sine of x looks like. And I'll put that over here in a lighter color anyways. Let's try it with this. If I were to graph y equals sine of x, I know that my amplitude is 1, so that means my range goes -1 to +1. We have marks along the x-axis here. Let's make it, here's pi over 2, here's pi, here's 3 pi over 2, here's 2 pi. And we want to take a look at this graph on the interval from 0 to 2 pi. So if I'm graphing my sine function, the sine function would include points like 0, 0, pi over 2, 1, pi 0, 3 pi over 2, -1, 2 pi 0. And if I were to graph it on this interval, it's going to look sort of like this. It's going to go along, pass through each of these points one by one, come along, and we would have one cycle of a sine function that looks like this. Now, the question is, what will our cosecant graph do? Well, the cosecant function, we said, is going to be undefined at any point where where sine is equal to 0. So that means we actually have vertical asymptotes anywhere where the sine graph would hit its x-axis. So that means 2 pi, pi, and even 0 are the locations of some of our vertical asymptotes. So we would label this right here. I'm going to label my vertical asymptote. Here are my 3 vertical asymptotes at x equals 0, x equals pi, x equals 2 pi. And if we follow along this pattern, what's going to happen? Well, we could say, all right, vertical asymptotes will occur at numbers like x equals, and we could just list off sort of a sequence here of numbers 0, pi, 2 pi, and so on. Another way of stating this is that x is equal to multiples of pi, where n is any integer. Okay, so while that is the graph of my sine or cosine function here, I'm going to shrink this down just a little bit. Okay, so my sine graph sort of lightened up right here a little bit. What's going to happen with my cosecant function? Well, what's going to happen is this. Wherever sine of x is equal to 0, we've got a vertical asymptote. Wherever sine of x is equal to 1, cosecant of x is equal to 1. I've got a vertical asymptote. When sine is -1, cosecant is also -1. Whenever the graph of the sine function increases, the graph of the cosecant decreases. So it's going to come along this vertical asymptote at 0 and then come towards 1. And then wherever the graph of sine decreases, the graph of cosecant increases. So it's going to increase towards this vertical asymptote over here at pi. The graph is going to continue to increase, but this time come along from beneath, go up to 3 pi over 2 and -1, and then decrease towards -infinity. And then the period would start all over again. So we'd get another cycle off to the right here if we wanted to, or we'd get another cycle off towards the left if we cared to put it. That might go like this, and we could show this function over and over and over again. But this is the graph of y equals cosecant of x. Let's take a look at y equals secant of x this time. And again, this time we're going to use the cosine function as our guide. So we recognize once again that secant of x is the same thing as 1 over cosine of x. And so we can show how this function will look if we know what the cosine of x is. So I'm going to go ahead and I'm going to mark off my graph using 1 and -1 along the y-axis. I'm going to mark off my horizontal axes here at pi over 2, here at pi, here at 3 pi over 2, here at 2 pi. Since it is a cosine function, that cosine function at 0 is always equal to 1. At pi over 2 is equal to 0. At pi is equal to -1. At 3 pi over 2 is equal to 0. And at 2 pi is equal to 1. Let's get a nice thin graph going this time. So my cosine function, if I follow the pattern right here, goes like this. Comes along, passes through each of these points in turn, follows this particular pattern over and over again. And his little tail over here goes on. All right, so what does our cosine function tell us? Well, in this case, our cosine function is going to tell us that, we're doing good, okay. Our cosine graph tells us that at cosine of x, we get 0 here. At pi over 2, cosine is 0, so that means it's going to be undefined. That is the location of a vertical asymptote of our secant. At pi, our value for cosine is -1, and at 3 pi over 2, cosine is 0 again. That gives us the location of another vertical asymptote, and then at 2 pi, cosine is equal to 1 again. Since secant is the reciprocal of this, we're going to say that our curve will follow along just like it did before, where cosine decreases, secant increases, and it increases towards its vertical asymptote here at pi over 2. It continues to increase from this side up along our vertical asymptote and up to pi -1, and then decrease again towards negative infinity at our next vertical asymptote at 3 pi over 2. Then it's going to decrease along the vertical asymptote and pass through this point. So if we go and look at one cycle of the function of secant, this is what it looks like. All right, the asymptotes, well, we've already seen that asymptotes occur at numbers like pi over 2 and 3 pi over 2. Take a moment and think, where would be another vertical asymptote? Well, if we went out towards the right, one more over here, we'd say, well, add pi to 3 pi over 2, we'll be at 5 pi over 2, and we would have another vertical asymptote. And if we went off to the left, we'd be at negative pi over 2 for another vertical asymptote. So what's happening here? Well, the pattern here is slightly different, but you see what's going on. Pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2 to be next, 9 pi over 2, and so on. So another way of stating this might be to say, well, all right, vertical asymptotes occur at any odd multiples of pi over 2. In the world of graphing, in pre-calculus, we say, all right, how do we get an odd number? Well, if n is any integer, just like I did this before with the sine graphs, if n is in the set of integers, -1, 0, 1, 2, and so on, then 2n plus 1 is always an odd number. So we take 2n plus 1 times pi over 2, and that would be another way, an alternate method of stating the location of these asymptotes. Okay, so this is our graph right here. Keep these in mind because we're going to graph some secant and cosecant functions here in my next few examples.